So I'm just jumping back and trying to explain Newton's method to you. Here's what is Newton's method? It's this. First of all, what is it for? He uses it for, you can adapt it to use it for some other things, but it's kind of for finding, and it's approximating. It's a numerical procedure for approximating the zero of a function. I'm going to write those words too. Newton's method is a numerical procedure. We haven't done too many numerical procedures. This is a good first one to do here. It's a numerical procedure for finding or approximating the zeros of a function. See, in math, we do a lot of things. The word is, and you've heard this word before, we do things analytically. And that means we're proving it exactly, kind of. So when we're estimating or approximating, that's different. We're not used to that a lot, but there's plenty of math involved with estimating and approximating. And this is Newton's method, a numerical procedure for approximating the zeros of a function. Here's the concept. If you have some function, by the way, the zeros of a function are, another word for the zeros of a function are where it crosses the x-axis or the x-intercepts. That's the zeros of a function. So I'm trying to find this zero of this function. So here's the game. Here's Newton's method game. Okay, and then I'm sort of deriving this for you. I'm explaining this to you. You start with an initial guess. You start with an initial guess. You just guess. You guess. So you guess. Oh, okay, maybe it's right here. Maybe it's x1. Okay. You plug that guess into the function. You take the derivative of the function and get this. By the way, the derivative of the function is the slope of the tangent line. You knew that. So you find the derivative of the function. You get the slope of the tangent line, and hold on. You guess an x value, you plug it into the function, which sort of gives you a y value here, f of x1. So now you have an x and a y value. You take the derivative and you get the slope of the tangent line, which would be f prime of x1, f prime of x1, the slope. And then watch what you do. You try to find the x-intercept of that tangent line. Now look, is the x-intercept of the tangent line going to be the x-intercept of the function? Is the x-intercept of the tangent line going to be the x-intercept of the function? No, but it's going to be close, especially if that initial guess was kind of close. The tangent line approximates the function pretty well, but not forever, right? Look, this tangent line is a good approximation for what this function is doing. Only around there. I mean, look at this tangent line. Is this tangent line a good approximation for what the function is doing? Not too well, not way the hell over here, no. But right around in here, it's kind of a good approximation. So finding the x-intercept of the tangent line is an estimate of finding the x-intercept of the function. Now, you don't like it, do you? It's kind of a bad estimate. So guess what you do? After you find that x-intercept of that tangent line, at first you call it x2, and then you do the procedure again. So it's a numerical procedure, and not only that, I'm going to use this word. It's an iterative procedure. Iterative. That means you perform another iteration. You do it again. A second iteration, maybe a third iteration, maybe a fourth iteration. You perform the procedure again. That's an iteration. It's an iterative. I don't know where the hell that word comes from. Watch, we do it again. So now watch, this x2, watch this. This x2 gets plugged into the function. We find the tangent line to the function at that point. We use it to estimate the x-intercept of the function. It's not right, but I use that, I call that x3. It's getting closer though, ain't it? You see how x1 and then x2 got closer, now x3 got closer. Now watch this. Plug in x3, find the tangent line on the function. Holy shamoly, look at that. That's x4. The more times you do it, it zeroes in. It's an iterative numerical procedure that converges toward the x-intercept after several iterations of this. You with me? Makes sense, right? It seems to make sense. I try to explain stuff well. All right, so now what's the formula? Watch. So now you got to sort of derive this formula. Let's go back to the very first time. What did I do? I plugged in that x1. Did I get a y? What was my y value? F of x1, right, you guys? So this was my point on the function. Now, I wanted the slope of my tangent line. So what did I do? I took the derivative, which is f prime of x, but then I plugged in x1. So the derivative with x1 plugged in is my slope. Now, hold on. Are you with me on this? Back to the, you got an x, you plug it in, you get a y. That's x and y. And the slope of the tangent line is the derivative. The slope of the tangent line is the derivative at that point. Are you guys okay? So there's a slope, there's a point. Can you get the equation of a tangent line if you have a slope and a point? Here I go. Derive the equation using point slope form. Y minus the y value equals the slope times x minus the x value. You guys okay? This is good old point slope formula. I got an x and a y value and a slope. This is my tangent line. This is my tangent line. Now what did I do after that? What did I do with that damn tangent line? Do you remember? Found its x-intercept. I found its x-intercept. How do you find an x-intercept of a line like this? You let y equal 0. So to find his x-intercept, I let y equal 0 and I solve for x to find his x-intercept. So here I go. This y is a 0 and I get this. And I want to solve for x. I think I'll divide by this derivative thing. I'll divide by this derivative. I'll get negative f of x1 over f prime of x1 equals x minus x1. I'm trying to solve for x, you guys. I'm trying to solve for x. So I think I'll add x1 over here to this side. So here's my x. It's x1 minus f of x1 over f prime of x1. And I don't know if you remember, but what did I call that x? Once I found that x-intercept, I called it x2. I'm going to write this formula up here. I'm going to write it backwards. I'm going to write it backwards. So this x-intercept that we're looking for is this formula, you guys. It's x1. It's your initial guess, x1, minus the function at x1 over f prime of x1. Listen, I could have walked in and said, here's the formula, you guys. But I wanted to explain it to you, which I did. And the thing is, I don't explain stuff to you if I don't think you're capable of understanding it. You can understand this. It's the equation of a line, and we're finding the x-intercept. You can totally understand this. That's why I bothered to explain it to you. You know? But the truth is, you don't have to understand it too much. This is your formula. This is Newton's method formula. Now hang on. If you plug x1 into this formula, that's your first guess. So what does that give you? It gives you x2. Now what did I say to do with x2? Do another iteration. I said do the whole goddamn procedure again, is what I said. And so watch what happens. That means you're sticking x2 into here. So now you have, minus f of x2 all over f prime of x2. And when you do that, what's that answer going to be? That's x3. And remember, it's going to be a better approximation than that first one. What if I wanted x4? I would plug x3 in there. Okay, so then, right? So then here's Newton's method. What Newton's method says is you plug xn into this. They just kind of generically say you're plugging xn into this. And if you plug xn into this, the answer you get is xn plus 1, the next x. That's how it worked. When I plugged in x1, I got x2. When I plugged in x2, I got x3. When I plug in x3, I get x4. This is Newton's method. And you do not have to memorize it. If I make you do this on some kind of a test or a quiz, I'll supply this formula for you. But you ought to practice it. And you kind of understand where it came from, perhaps. But the truth is, you don't really have to understand where it came from too much. You can practice using it. I wonder if we can practice using it real quick. Let's try it for this function right here. So now what am I doing? What the hell am I, what's Newton's method good for? What's the goal there? I'm going to go do this damn formula, but what's the goal? Oh, I'm trying to find the zero. I'm trying to find the x-intercept. Now, okay. Do we know the x-intercept? Real quick. Analytically, I know we're going to do Newton's method, right? But analytically, do you know the x-intercept? You set it equal to 0, you move the 2 over. I guess there's a couple x-intercepts. What are they? Plus and minus the square root of 2. All right, let's say we're looking for this positive square. So, here, by the way, here's the picture. It's this parabola and these x-intercepts. So let's say we're looking for this one. So I want to do Newton's method. So Newton's method needs the function. What else does it need? What else does it need? It needs the function. What else does it need? It needs the derivative. What's the derivative? What's the derivative? 2x. Okay, it needs the derivative. And then what else does it need? I need an initial guess. So that'll be my x1. That'll be my initial guess. What do you think you want to do for your initial guess? Especially now that you know the answer, What would you use for an initial guess?
1.
I would use 1, sure. By the way, a bad initial guess, and Newton's method could go wrong, okay? You kind of need a close initial guess to get it to work. So it doesn't always work, I guess. There's some exceptions when it doesn't work too well. So a good initial guess helps. So you're right, we'll use 1. Okay, here we go then. Here I'm going to do this formula. In order to get x2, I'm plugging in x1. So here's what that means. I'm going to plug in a 1 right here, right? What does this say? Plug a 1 in your function? I'm going to even write that. I'm plugging a 1 in the function and divided by plugging a 1 into the derivative, right? Now, let's do that. 1 minus, what happens when you plug a 1 in your function? A 1 in your function. 1 minus 2. You get a negative 1 over, when you plug a 1 in your derivative, you get a 2. Okay, cool. That's pretty easy, you guys. That's 1 minus a negative 1/2. That's 1 plus 1/2. What is this x2? 1.5. By the way, what's the real answer? Square root of 2. And by the way, the square root of 2 is 1.414, blah, 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 right? So there's the real answer. So, hey, our first guess was wrong. But one iteration of Newton's method got me a pretty good damn guess. Let's do it again, though. So what does that mean? I want to find x3. How do I find x3? I feed x2. I feed my answer from the first problem into the formula again. It's feeding the answer back into the formula. That's the iteration. That's where the word iteration kind of comes in. You get the answer and you feed it back into the formula. I mean, this is great for computer programming. In fact, you might take a class someday where somebody asks you to write a program for Newton's method. I mean, you might. right? Some engineering class somewhere, they refer to stuff like this. They refer to these numerical procedures for good computer programming practice. Okay, what am I doing? Oh, I'm plugging in a 1.5. I'm plugging in a 1.5. That means I'm plugging a 1.5 into the function, and I'm also plugging a 1.5 into the derivative. I'm sorry, I wrote it all like this, but here I go, and now I got to do it. 1.5 into the function. Okay, I can do this in my head. That's 2.25 when you square it, and when you subtract 2, it's a 0.25 over 1.5 in the derivative. 1.5 in the derivative is 3. So it's 1.5 minus this little fraction. Why don't you help me and tell me the answer? 1.41666. Is that what she said? Okay, hey, we're getting closer to the real answer. Aren't we? It's working. It's working. Maybe we should do it again. Now, here's the problem. I really don't like, here's the problem. You start feeding these numbers back in. I mean, you don't really want to round these. I mean, rounding these is going to, affect your answer. So I would try to feed this number back in without rounding it, which that means I got to write 1,000 sixes, or more than 1,000 sixes. Well, maybe that you're saying there's a fraction equivalent to this. Yeah, that could help. That helps you not round. Well, or if you just took it out about 5 or 6 decimals, maybe that's good enough. I'm trying to avoid you rounding too much because that'll throw off your answer, right? So if you took it out 5 or 6 decimals and rounded it, maybe you're okay. But you are suggesting that it's actually a, what is it? 17/12. You're a 17/12, huh? Yeah, well, that might help. So then I could find x4. I'm going to quit, though, now. I'm going to quit. And if I was you, I would work in 5.1 and get good at basic antiderivatives. But if you wanted to ease back into 3.8, you could check your homework list, and you could maybe try a Newton's method problem. I want to help you with, I'll help you with a little more of this Friday. And I'll probably ease into 5.2 Friday.